Welcome to our video all about the cosine and sine and the unit circle. This is one of my favorite topics to teach because I get to introduce to you the importance of cosine and sine and why they're the building blocks of all of our trig functions on the unit circle. There are a total of 6 trigonometric functions, and you've probably learned 3 of them in geometry, which are cosine, sine, and tangent. Cosine and sine are the x and the y of any point on our unit circle, and we're going to be talking about their importance throughout this video, as well as deriving the reason why they're the x and y of our coordinate points. Here is the unit circle in all of its glory. I took a bunch of screen grabs from your textbook because, frankly, theirs looks better than anything I could ever draw. Plus, do a quick Google search of the unit circle and you'll find millions of these. It's out there. You can easily find the cosine and sine of all of these important points on the unit circle. The idea behind this video is learning the y's behind it. I already said that the cosine is the x value and the sine is the y value of any point, or any angle rather, on our unit circle. So if I asked you to find the cosine of pi over 6, it's the x value. It's root 3 over 2. If I asked you to find the sine of 3 pi over 4, it's the y value. It's root 2 over 2. We are going to talk about why these values are here and use the patterns of the unit circle to be able to derive them and find them ourselves. The patterns that we talked about in the last video are the families. We have the pi over 6 and pi over 3 family. They're in the same family because if you double pi over 6, you'll get pi over 3. The other family of points on the unit circle is the pi over 4 family, which is halfway through each quadrant here. You could also make a case that there's a third family, which is the family on the axes. Those are the easiest to find. We will be focusing on the pi over 6, pi over 3 family, and then the pi over 4 family, and see why all of their coordinate points in the pi over 6, pi over 3 family involve root 3 over 2 and 1/2, or negatives, and then why the pi over 4 family, all of their coordinates on the unit circle are root 2 over 2, or negative root 2 over 2. Yes, there's a ton of patterns here, and we're going to use geometry and the Pythagorean theorem to figure out why. We will begin with the pi over 4 family. That is any angle that has over 4. So if we take a look in quadrant 1, I just zoomed in on the unit circle, here's quadrant 1. If we take a look at theta equals pi over 4, which is 45 degrees, we see that the coordinates on the unit circle here at this point are both root 2 over 2. Therefore, the cosine and the sine of pi over 4 are both root 2 over 2. I'm going to explain to you using geometry and the Pythagorean theorem why that is. We see here on our unit circle when we focus on pi over 4, aka 45 degrees, if we go out, hit the coordinate point, call it P equals xy, and then drop a perpendicular, we've created an isosceles right triangle. We know that it is isosceles and right because we dropped a perpendicular, therefore creating a right angle. We know that's isosceles because, as we recall from geometry, if we have a right triangle, the other two acute angles must add to 90 degrees, or pi over 2 if we're talking about radians. Therefore, because this is 45 degrees, aka pi over 4, this angle must also be 45 degrees. We also know, if we zoom in on this triangle that we've created, that this horizontal distance is the x-coordinate of our coordinate point P, and this vertical distance is the y-coordinate because we've traveled x units to the right and y units up to get to this coordinate point xy. Let's prove why both x and y are root 2 over 2. We can start with labeling the hypotenuse of our right triangle 1, because the hypotenuse is the radius of the unit circle, which is 1. Then the next thing that we know is the Pythagorean theorem relates the side lengths of right triangles. The Pythagorean theorem is a squared plus b squared equals c squared, where a and b are the lengths of the legs and c is the length of the hypotenuse. In this case, x and y are our legs, so we can write out that x squared plus y squared equals 1 squared. Now, because it's an isosceles triangle, we know that x and y are the same length, so I'm going to call them both x. Yes, we could call them both y if we wanted, or call them both a, whatever we want. I'm just going to use x instead. 1 squared is just 1. Combining like terms, I have 2x squared equals 1. Dividing by 2, I have x squared equals 1/2. And then taking the square root of both sides, I have x equals plus or minus the square root of 1, which is 1, over the square root of 2. Now in mathematics, we do not want to write a denominator with a root in it. Therefore, we need to rationalize, so we'll multiply the numerator by root 2 and the denominator by root 2. 1 times root 2 is root 2. We still have that plus or minus. And root 2 times root 2 is root 4, which is plain old 2. Now, this is a length, and it is a positive length because all lengths are positive, but on the coordinate plane here, we're moving to the right in this case, so it is a positive direction. If we are moving left, the x-coordinate would in fact be negative. So in this case, we are going to just go with the positive root 2 over 2. So we can come to the conclusion, we know that x is root 2 over 2, and because x and y are equal, we know that y is root 2 over 2. So we have a generalization, and we have any right triangle on our unit circle that has a reference angle, we'll talk more about that later, of pi over 4, has obviously a hypotenuse of 1, and leg lengths of root 2 over 2. If you also recall back from geometry, which even if you don't, it's okay, you might have heard in mathematics SOHCAHTOA. Now in this video, we're only going to focus on the SO and the CA because TOA is tangent and we'll get there later. SOHCAHTOA, you may not have seen it written like this, but it is an acronym, I believe. It's a way that we can help remember what it means. The S stands for sine and the C cosine. The O and the H are opposite and hypotenuse, and the A and the H stand for adjacent and hypotenuse. So if we look at our pi over 4 triangle, and we want to find the sine of pi over 4 and the cosine of pi over 4, we see the cosine of anything, this angle down here, pi over 4, the cosine is adjacent over hypotenuse. The adjacent side is root 2 over 2, and the hypotenuse is 1. Therefore, putting root 2 over 2 over 1 is just root 2 over 2. In order to find the sine of pi over 4, sine is opposite divided by hypotenuse. If we take this angle here, our opposite side is root 2 over 2. The hypotenuse is still 1, so putting anything over 1 doesn't change it. Our opposite side is root 2 over 2. This is an alternate way of looking at sine and cosine and seeing why it is the x and y coordinate points. Because our hypotenuse is 1, the adjacent side of our angle in standard form on the unit circle is going to be the x-coordinate. If we take a look at sine, the opposite from our angle, theta, in this case pi over 4, that is the vertical distance, or the y-coordinate. That is why the cosine of any angle on the unit circle in standard form, the cosine is the x-coordinate of our point, and why the sine of any angle in standard form on our unit circle is the y-coordinate of that point on the unit circle. Next, we want to focus on our pi over 6, pi over 3 family of angles. If you take a look at our, again, a snip from the unit circle in quadrant 1, we have the angle pi over 6, which is 30 degrees, and then we have two of those, 2 pi over 6 or pi over 3, which is 60 degrees. These are related because we have the famous 30, 60, 90 triangles, just like we had the famous 45, 45, 90 triangles for the pi over 4 family. So if we take a look at pi over 6 and pi over 3, we see that the x and y coordinates are root 3 over 2 and 1/2, and then swapped up here for pi over 3. Let's prove why that is, focusing on the pi over 6 right triangle. This derivation takes a little bit more imagination. No, I am not calling myself imaginative or creative. I didn't come up with it. I just think it's really cool. Let's take a look at this pi over 6 angle here, which is of course 30 degrees because 6 of them make up one whole pi, or 180. So if we take a look at this pi over 6 or 30 degrees, the only thing that we know in this case is the hypotenuse of this right triangle, which is 1. We do not have the luxury of knowing that the sides are equal because they're not. This is not an isosceles right triangle, so it's a little bit more difficult to come to this conclusion. But in order to do so, we are going to extend this angle this 30-degree or pi over 6 angle, we're going to double it and move down into quadrant 4. So what I'm going to do is I'm going to move down another pi over 6 or another 30 degrees, thus creating an entire angle of 60 degrees or pi over 3. And this coordinate point here I'll call Q. It doesn't really matter what we call it, but I know that the x coordinate is going to be the same as P, but the y coordinate is just going to be negative because of the symmetry. Now, what have we just done? We have now created another special type of triangle, not an isosceles, but an equilateral. Because this entire angle here is twice pi over 6, it's twice 30 degrees. It's now 60 degrees. Now, before, because this was 30 degrees and this is 90 degrees, we knew this was 60 degrees already. 30, 60, 90. So this is now 60 in total. This is 60, and therefore, because they have to add up to 180 degrees, this is also 60 degrees. The reason that we do this to derive is because now we have an equilateral triangle. I know that this length is 1, but more importantly, I know that this vertical length over here is 1. Because of the symmetry, if we know this whole thing is 1, what do we now know this half is? Half. So we did all of that extending to an equilateral triangle to come to the conclusion that this other side length here, this y coordinate, is 1/2. Now we no longer need this entire thing. We can use the Pythagorean theorem now that we know two side lengths of our right triangle. So let's now solely focus on the triangle that I've outlined in orange, and we can zoom in on it down here and write what we know. We know, of course, the hypotenuse of it is 1, and we know that this side length, the vertical side length, is 1/2. Let's use the Pythagorean theorem to find x. We know that x squared plus 1/2 squared equals 1 squared. So we know that x squared plus 1/4 equals 1. Subtracting 1/4, we'll have that x squared equals 3/4. And square rooting both sides, we'll have that x. Again, it's going to equal plus or minus, but because this x coordinate moves to the right, because we're in quadrant 1, we know that it's positive. So I'll just take the positive version, √3 over the square root of 4, which is 2. So our x coordinate is √3 over 2. So once again, let's go ahead and generalize this a bit. We have our pi over 6, pi over 3, 90 triangle, which again is 30, 60, 90 in degree form. And we know that the hypotenuse is, of course, 1 because it's the radius of our unit circle. We know that this side length is 1/2, and this side length over here is √3 over 2. Now, what's bigger, 1/2 or √3 over 2? Well, they're both over 2, so what's larger, 1 or √3? √3 is larger, so the √3 over 2 side length is larger, and that makes sense because it's opposite the larger angle, which is pi over 3 or 60 degrees. Now we can use our cosine and sine, so and ca, in order to find the cosine and sine of both of these angles. Let's start with pi over 6. So we'll find the cosine and sine of pi over 6, and we can use so ca toa, but cut the toa because we're not focusing on tangent in this case. So the sine of any angle is opposite over hypotenuse, and the cosine of an angle is adjacent over hypotenuse. This is basically proving why the sine is the y-coordinate and the cosine is the x-coordinate. So let's start with cosine of pi over 6. Here's our pi over 6 angle. The adjacent side to it, the side next to it, that's not the hypotenuse, is √3 over 2, and the hypotenuse is 1. So our cosine of pi over 6 is √3 over 2. In a similar way, the sine of pi over 6, the opposite over the hypotenuse, is 1/2. Then we want to focus on pi over 3, our 60 degree angle. We can do that without doing a whole nother derivation because pi over 3 is part of this right triangle. So now we're looking at it from the perspective of pi over 3 up here. No, it's not an angle in standard form on the unit circle, but that's okay. We could easily move this around so it would be down here. Let's take a look and find the cosine of pi over 3. Cosine is adjacent over hypotenuse. From the perspective of pi over 3, the adjacent side, or the side next to it that's not the hypotenuse, is 1/2. So 1/2 over 1 is just 1/2. And the sine of pi over 3, using the similar method, is √3 over 2. So we have successfully derived the general 30, 60, 90 right triangle side lengths using a bit of creative geometry, the Pythagorean theorem, and, of course, now trig. Now, so far we've done a ton of derivations. This is the main idea of this video, or one of them, I suppose, is that for any angle theta in standard form on the unit circle, the cosine of theta is the x-coordinate, and the sine of theta is the y-coordinate of the coordinate point that it reaches on the unit circle. So here is our main point down here. xy is cosine sine. This is the other main idea of the video. We have already gone through all the y's of this through derivation, so go ahead and pause the screen and make sure that you have this written down and you understand what we're writing down. Now we're going to find some exact values of these common points made from the angles on the unit circle. So we want to find the cosine of 3 pi over 4. 3 pi over 4 is literally 3/4 of the way to pi. And remember, pi is over here at the 180 mark. Here's our, oh, that wasn't too bad. Here's our unit circle, and over here is pi. So 3/4 of the way to pi, it's part of our pi over 4 family. Anytime we have an over 4, we know that we're splitting a quadrant in half. And so we're splitting the second quadrant in half right here. So we want to know what is the x-coordinate of 3 pi over 4, the cosine of 3 pi over 4. Well, let's think about what our reference angle would be. The reference angle is going to be an acute angle that is the quickest way to the x-axis. In this case, our reference angle would be what's left over here to get down to the x-axis. And if we're 3/4 of the way to pi here, 3/4 pi, the reference angle here is pi over 4. A reference angle is always going to be pi over 4, pi over 6, or pi over 3, which is why those three are so important. So our reference angle here is pi over 4. And if we think about that, we have a pi over 4, 90 triangle. And using what we know and what we found in this video, we know that the x-coordinate of those and the y-coordinate is both root 2 over 2. Now, we do not know whether it's positive or negative, so we just know root 2 over 2 and root 2 over 2. We have to think about the quadrant that we're in. Because we're in quadrant 2, our x-coordinate has to go to the left and our y-coordinate is up. Therefore, because our x-coordinate's moving to the left, because we're in quadrant 2 here, our x-coordinate is actually negative root 2 over 2. That means that the cosine of 3 pi over 4 is negative root 2 over 2. So we use the fact that the reference angle is pi over 4, and we know that the pi over 4, 90 right triangle has root 2 over 2 as the x and the y coordinates. We then used the fact that we knew that 3 pi over 4 was in quadrant 2 to understand why the x-coordinate is negative. In number 2, we want to find the sine of 5 pi over 6. So once again, I'm going to sketch out my unit circle, and we want to think about where 5 pi over 6 is. Well, similar to problem 1, 5 pi over 6 is almost a whole pi. It's pi over 6 away from pi, and pi is over here, all the way halfway across the unit circle. So 5 pi over 6 is almost going all the way there, but not quite. We still have pi over 6 to go. So our reference angle, the angle that most closely gets us to the x-axis, is pi over 6. And because we're looking for the sine of 5 pi over 6, we really care about the y-coordinate. What do we know about the pi over 6, pi over 3 right triangle? Well, we know that pi over 6 is 30 degrees, so it's a 30, 60, 90 right triangle. And as we recall, if we take a look at that right triangle and we zoom in, because this one's a little bit more complicated because we have different side lengths. So we have a pi over 6, pi over 3. This side length is 1/2. This side length is root 3 over 2. And of course, the hypotenuse is 1. What we care about is the y-coordinate here, which is 1/2. It is in the second quadrant, and therefore our y-coordinate, we have to go up to get there. Therefore, the sine of 5 pi over 6 is positive 1/2. Now, you would argue with me, Mrs. Dalmash, can't you just look at the unit circle and figure this out? Yeah, you totally can. And to prove your point even better, I just Googled a different unit circle. There, like I said, there's a ton of them out there. The point behind this is not that I can just give you a unit circle and tell you the cosine's x and the sine is y. I wanted you to see why that is. And as students in the STEM field and future engineers, scientists, mathematicians, heck, even teachers maybe, it is important to know the whys behind things. It's important to know why something works, how it works, and to be able to explain it. Yes, I can give you a sheet of paper and I can tell you, well, just take a look at 3 pi over 4 and the x-coordinate's negative root 2 over 2, and look at 5 pi over 6 and the y-coordinate's 1/2. Great. But it's important to know the whys behind these things. Sure, robots are going to be able to do a lot of this stuff and can do a lot of stuff for us right now, but who's making the real money and who has the real power are the people that program those robots. My point being that it is important to be able to create and not just to use. It's important to know why and how and not just what. Therefore, I grant you permission to just use the unit circle and to figure it out, but hopefully it makes a little bit more sense why cosine is x and sine is y, and how to use those reference angles and those cool families and patterns to figure this out. The last thing that we're going to look at are angles that are actually on the x and y axes and those that do not form a right triangle. So if we take a look and at number 1, we want to find the cosine of pi. Well, we know that pi is 180 degrees, and therefore on our unit circle, that one not drawn as well, pi is over here. So this is the angle of pi. It's a straight angle, and we cannot like drop a perpendicular out here and create anything. So therefore, in this case, we have to just realize, hey, this is on an axis. It doesn't have complicated coordinates. This coordinate point over here, it's 1 unit to the left because it's the unit circle. We haven't moved any units up or down, so the y-coordinate has to be 0. So since we moved 1 coordinate to the left and 0 units up or down, the coordinate points at pi are -1, 0. The cosine, as we've derived throughout this video and talked about, is the x-coordinate, so the cosine of pi is -1. In a similar way, to find the sine of pi over 2 is halfway to pi. It's right here. The sine is the y-coordinate. If we think about the coordinates of pi over 2, we have moved 0 units left or right, but 1 unit up because we're on the unit circle. And so the coordinates at pi over 2 are 0, 1. Therefore, the sine of pi over 2 is 1. Thank you for going on this journey with me and explaining why the cosine and sine are the building blocks of this beautiful, beautiful circle in trigonometry, the unit circle.